Hi all, is the screen visible?
Yes, ma'am.
All right. So in the last lectures, we have seen the various methods, say the bisection, Newton's, and secant method to find the approximation of the root of nonlinear equation fx is equal to 0, right? So in today's lecture, we are going to see another class of iterative methods, but the methods which we will be deriving is by rewriting this given equation, let's call it 1, into a fixed point problem. Okay, so what is a fixed point problem? So this can be reformulated as x is equal to gx. So let's give it a equation number 2. Okay, we will discuss that how can we find g, like given equation fx is equal to 0, how can you write down the equation in the form x is equal to gx? That is what are going to be the choices of the g. So that we will discuss in a moment. So, but first let's understand that what is a fixed point. Okay, so this problem is basically a fixed point problem. Okay, fixed point. So do you guys understand what is a fixed point? So how, what is a fixed point? How do we understand the fixed point of any function? So suppose here we are talking about the function g, right? So what is the fixed point of the function g? It's nothing but like you take each function of, yeah. Yes, please continue.
It's a point on the domain where the value of function doesn't change.
Okay, actually,
That means g of x equal to x.
exactly. So basically, each solution of this equation x is equal to gx is called a fixed point of g, right? That is what we are looking for. We are looking for, so I can write it in a form that, say, if we say that x star is a fixed point of g, this means that it will satisfy that x star is equal to g of x star, right? So our next iteration method is based on this new formulation 2. Okay, so what is a fixed point iteration? So again, as we have seen in the other iterations method, so we start with the initial guess x naught. And we generate a sequence of iterates. Let's call them x1, x2, x3. So which are basically the approximation of the fixed point of g, that is the x star. So note that if x star solves this, so this will also satisfy f of x star is equal to 0. Okay, so the fixed point of g is going to be the solution of the fx is equal to 0. All right, so how do we find the x1, x2, x3? So knowing x naught, or in general knowing xn, I'm going to compute the xn plus 1 by evaluating g at xn. Okay, so this method is known as the fixed point iteration method. Now, just give me a moment. Yeah, so once we have decided the right choice of the G, we will be just computing the iterative sequence using this iteration formula. And now what we will be understanding that what choices of the G we have to take, right? And whether this sequence of the iterates which we are going to construct using this fixed point iteration method, that is going to converge to the fixed point of the G, right? And you can, of course, note that this iteration methods depend on the choice of the G, right? So the convergence of the sequence, which we will get here, that is xn, this will also depend on the choice of the G, right? So let's try to see that, first of all, what are the choices of the G we can have? Like, how can we write the given equation fx is equal to 0 as x is equal to gx? So we have fx is equal to 0, and what we want to write it, we want to write it in this form, x is equal to gx, right? So you can see that we can have the gx as x minus fx, right? So if you take gx is equal to x minus fx, then x is equal to gx is equivalent to fx is equal to 0, right? We can also have gx as x plus, say, 2fx, or in fact we can have x plus any constant times fx where c is not equal to 0, right? So this will also give you back fx is equal to 0, x is equal to gx. Okay, we can also have gx as x minus fx divided by f prime x, assuming f prime exists and f prime of x is not equal to 0. Okay, this is another choice of the gx which we can have, which will again give back the equation fx is equal to 0. Okay, so if you try to use these different choices of the G, you will see that you're not just getting one iteration method, it's just a class of the iteration methods, right? So let's just try to take one example and try to see what is happening with these different choices of the G. So I'm going to take one example. So let's consider that we have to solve this equation, x square minus a is equal to 0. Okay, and a is strictly positive here. So what is fx here? Fx is x square minus a. So now we can reformulate this problem as x is equal to gx form in the following way. So we can write here x is equal to, so I'm just going to add x both sides. So what I will have, x square minus x plus x minus a, right? So here basically what is gx? Gx is x square plus x minus a, or more generally we can have it as x square minus a. I'll multiply with any constant, non-zero constant, right? So in this case, gx will be x plus c times x square minus a basically, right? Another choice of the fixed point problem you can have here is that x is equal to a by x. Okay, so this is a gx here. And we can also choose based on this third choice, that is, I can write my fx is equal to 0 as x is equal to 1 by 2 x plus a by x. Okay, so suppose we have these choices of the gx, okay, and we want to see whether, like, which choice is correct, right? We can get a plenty of the choices of the G in this way, right? But we have to get hold on the one right choice of the G, for which we can make sure that this sequence will converge to the fixed point of the G. So first of all, G should have a fixed point, and then the sequence of the iteration should converge to the fixed point of the G. So let's consider the same example for a particular choice of the A. So let's take A is equal to 3. Then we know that x square minus 3 is equal to 0. Its solution is x is equal to root 3 plus minus root 3. So I'm just considering the plus root 3 here, one of the roots, and which is approximately 1.732. Okay. Now suppose I have these various choices of the G from these cases A, B, and C. So use these choices of the G and try to use the fixed point iteration method to generate the iterative sequence. So I'm going to consider my n as, so I start with x0. So I will generate xn's. So now xn's I will generate using different cases. So I will take gx as this. That is, I will take the case A here. Okay. And then I will also generate the sequence xn using the second choice of the gx, which is this. And then I will also generate the sequence xn using this choice of the gx. And see what happens to those sequences. So I will start with the same initial guess. So I'll take x0 is equal to, so I want something near to the root. So I'll take 2 here. Okay. And you try to generate the xn's using xn plus 1 is equal to g of xn. Okay. That is, my x1 is going to be g of x0. So I'm going to take g at x0 first as this. So what is the sequence? Okay, initial root is the same, 2, 2, 2 in all three cases. Now you use the first choice of the G and try to generate the sequence. So that is G of x1, which is going to be 3. You can just find it out. And then, so this is, G of x0, and x2 will be G of x1, which will be 9. Okay, you just use this formula for the G and try to generate this sequence. Likewise, you will get is next entry will be 87, and in this way you can find the other entries. Okay, now you use the gx, which is given by the case B. So here x1 is going to be g of x0. So x0 is 2, so you can simplify this. This is going to be 1.5, and likewise you can compute the other entries. So this will be 2 again, and this will be 1.5 again, and this way you will get the sequence. Okay, and now let's try to take the case C, where gx is given by this, and try to generate the sequence of the iterates. So here again, x1 is going to be g of x0, which will be 1.75, and x2 is g of x1, which will be 1.732, some other entries. So this will be 1, 4 something. And then you generate the next iterate, x3 will be 1.7320, and further entries will be there. Okay. And likewise, you can generate the other iterates. So one thing you can clearly see, what can you say about the convergence of this sequence xn, which is arising from the case A?
Divergent.
Yeah, it doesn't seem to converge to the root 3, right? It's rather diverging, right? Likewise, if you observe the case B, so the sequence is like oscillating. You just go to 2 and 1.5, 2 and 1. This is the way it will be behaving, right? And the case C, you can see that it is converging to the 1.732, right? So it basically depends on what choice of the G you have. That will depend, first of all, whether you are going to have the fixed point of the G and the sequence of the iterates which you are going to generate using the fixed point method, whether that will converge or not. So it very much depends on the choice of the G. So basically we have now the following questions to be answered. So the first question we can ask, that what conditions on the G we have to have so that there exists a fixed point of G in, say, let's fix the interval to be AB. Okay, suppose we are in the interval AB. And if it exists, whether it is going to be unique. Okay, so once we have this information, that once we get this information that okay, there is just a unique fixed point for the G, then we can ask whether the sequence of the iterates using the fixed point iteration method that converges to. So if I call the fixed point as, so if I call x star, suppose we have answered the first question and we could get hold on the fixed point of the G, then the sequence of the iterative sequence that converges to x star or not, right? And suppose if we could answer the convergence part also, that is to say the sequence xn converges to the x star. Now what is the order of the convergence, right? That's the third thing we have to analyze. So suppose we could answer the second question as yes, then what is the order of convergence, right? So these are the questions we will try to answer. So first of all, let's see that under what conditions we can make sure that there will exist a unique, there will exist a fixed point of the G and that is going to be unique. So I'm going to state this as a lemma here. So let's take G to be a continuous function. On the interval AB and assume that G takes the interval AB to the interval AB, meaning that Gx is going to lie between A and B for all x's in this interval AB. So there's another notation used for the same thing. So this basically says that the G sends the interval AB to the interval AB. Okay, so this is another notation used for the same statement. Then x is equal to Gx. This has at least one solution. In the interval AB. Okay, so that is if G is sending the interval AB to the AB, then you can ensure that there's going to exist one fixed point of the G in the interval AB. Now this is the existence part. Now what we need for the uniqueness. So if in addition,
chronicity.
G is continuously differentiable, on AB, and there exists a constant rho which is strictly less than 1, such that mod of G prime of the X is less than or equal to rho, which is strictly less than 1 for all x's in this interval AB. Then the fixed point of G is unique. Okay, so let's try to prove this. The proof is very simple. So the information, let's just try to see the existence part first. So for the existence part, what is given, I'm just going to use this information that the G sends the interval AB to AB. That is, if X is in the interval AB, then the Gx is also going to lie in the same interval. So now what we have to show that there's going to exist at least one fixed point in that interval AB, right? So now if you have, suppose we have GA is equal to A or GB is equal to B. Because we know that Gx is always lying between the interval AB Suppose any of these two cases occur, then of course we are done, right? We have found, so if GA is equal to A, then A is going to be the fixed point, or if GB is equal to B, then B is going to be the fixed point, right? So if this happens, then we are done. So we assume that GA is strictly greater than A and GB is strictly less than B. Okay. And now what I will do, I will define a new function, Px, as Gx minus X. And note that G is given to be continuous, so this P is going to be a continuous function on AB. And what can you say about the P at A?
Greater than 0.
Positive.
Greater than 0. And what will happen to the P at B?
Negative.
Less than 0.
So now can you complete the proof? Can we say that just what I should use here so that I can guarantee that? So basically, if we want existence of a fixed point of G.
Bisection method.
Bisection method.
Bisection method.
No, we are at the continuous level. There's no habit here.
Intermediate value property.
By IUP.
Right, so you can use the intermediate value theorem here. Therefore, by intermediate value theorem, okay, so I've used this notation before, IVTs for the intermediate value theorem, so I hope you guys are familiar with it. Let me write it. Intermediate value theorem. There must exist a root of the phi x in the interval AB, right?
Yes.
You must have a root, let's call it to be x star, in AB. That is, what do we have is that phi of x star, this is equal to 0, or which basically says that x star is equal to g of the x star. Okay, so this means that x star, so this implies there exists okay, so the existence part is okay, right? So we have found one fixed point of G in the interval AB. Okay, just using the condition that GA is taking the interval AB to the AB. So sorry, the function G is taking the interval AB to the interval AB. Now let's try to argue the uniqueness part. So what is okay? So what do we have to do if we want to show that the G will have a unique fixed point in the interval AB? So how should we proceed?
Two fixed point. Then we saw that two are equal.
Right. So we start with the two fixed point and we try to show that they both are same. Right. So suppose x minus gx is equal to 0. This has two solutions. Let's call them x star and y star in the interval AB. Okay. Then, okay, let's write down what is given to us. So what is given to us is that the g prime of the x is less than or equal to rho for all x's in this interval, and rho is strictly less than 1. Right. So given is that g prime of the x is less than or equal to rho for all x's in this interval AB, and rho is given to be strictly less than 1. Okay. So we have to show that x star is equal to y star, right? If we have started with two fixed points. So let's consider this difference, x star minus y star, the modulus of that. Okay. So what we know about the x star, that this is a fixed point. So this is going to be the same as g of the x star. Now the same thing we know for the y star, that this is also a fixed point. So y star will be the same as g of y star. Now what should I apply here? You have been given some information. So how should I use that information here?
Minus x star minus y star. So,
What I have to apply here?
Mean value theorem.
I can apply the mean value theorem.
Yes, ma'am.
So if I apply the mean value theorem, I will have the existence of some xi such that this term will be the same as g prime of the xi times x star minus
Y star.
y star, where xi lies between
x star and
X star and Y star.
x star and y star.
y star.
Now we have been given that g prime of the x is less than or equal to rho for all x's in AB, and xi is lying between x star and y star, and x star y star both are in AB, so xi will also be in AB. So this is going to be less than or equal to rho times mod of x star minus y star, because rho is strictly less than 1, but of course this is 0, greater than 0, right? Because g prime, it is always greater than or equal to g prime of the x. This is always greater than or equal to 0. So what I have got from here is that 1 minus rho times mod x star minus y star this is less than or equal to 0, right? And rho is given to be strictly less than 1. Okay, so what I conclude from here, so this quantity, so rho is given to be strictly less than 1 and greater than 0. So 1 minus rho is going to be a positive quantity. So what we have is that mod of x star minus y star is less than or equal to 0, but mod of x star minus y star itself is a positive quantity. So the only choice what we are left with is that mod of x star minus y star has to be
0.
right. So which implies that x star is equal to y star. So which means that we have a unique fixed point of G. Okay. So what we have to see to have the existence. So what are the conditions we require on G to have the existence and uniqueness of the fixed point? That it should take the interval AB to the AB, and it should be, its derivative should be strictly less than some quantity which is strictly less than 1. Right? So we will try to rephrase these conditions again. But before that, let's try to see what happens to the, suppose we have got hold on the correct choice of the G. Whatever the condition we require, we have on the G, and we have got that there exists a unique fixed point of G. Now what happens to the iterative sequence, fixed point iteration? So consider fixed point iteration, which is given by, so the iterative sequence will be xn plus 1 is equal to G of xn. N is greater than or equal to 0. So let's try to understand the convergence of this sequence. So whether this sequence is going to converge or not. So my first, I'm only assuming the requirements what we have in this lemma. Okay, so under these requirements on G, let's try to see whether the sequence will converge or not. So the first thing which we will try to observe, that if we start with x0, which is in the interval AB, then the complete sequence which we are going to generate using this iteration method, that is also going to be in the interval AB. Right? So which is very obvious to observe, that what is going to be x1? x1 is G of x0, right? And x0 is in AB, so of course this is going to be in the interval AB, because G takes the interval AB to AB, right? So if you just use the same arguments, just you can use the induction arguments here. So you can make sure that if xn is in the interval AB, so this will imply that xn plus 1, which is nothing but G of xn, this is also in the interval
AB.
Right? So this means, so you can use the induction argument, and what we will get is that xn is going to be in the interval AB for all n. Okay. So, and what is going to happen to the convergence of this sequence? So we have to analyze what is happening to the x star minus xn plus 1. Right? So let's try to see what is given to us. Is that xn plus 1 is nothing but G of xn. Right? And what is x star? X star is a fixed point. Right? So this means that x star is the same as G of
X star.
Okay. So again, I'm going to use a similar argument as we have used in the uniqueness part. So this is going to be less than or equal to. So you can apply the mean value theorem,
Yes.
and
Right.
getting that this will be less than or equal to some rho times x star minus xn. Right. So I've skipped one step. You apply the mean value theorem, and then you use this property that mod of G prime of the x is less than or equal to rho. Okay, so this is what we have got. So you can further use the induction process. So this will be less than or equal to rho squared times x star minus xn minus 1. And if you repeat this process, so what will happen? So I'm going to write for x star minus xn, because I want to see the convergence of xn to x star, right? So instead of the xn plus 1, I'm going to consider xn here. So this is going to be less than equal to rho times of x star minus xn minus 1, which will be less than equal to rho square times x star minus xn minus 2. And if you repeat this process, I'm going to go up to the x naught. So what I will get is that rho raised to power n mod x star minus x naught. Right? And what does this imply? This implies that if you take as n tends to infinity, rho is strictly less than 1,
0.
going to go to 0, and which will imply that xn will converge to
X star.
X star.
right? So the sequence which we have got using the fixed point iteration, it converges to x star. And what is going to be the order of convergence here? What can you say using, can you say something using this argument?
Linearly.
1.
So it's a linear convergence here, right? Because we have taken rho is strictly less than 1. So the sequence xn converges linearly, and the rate of convergence is rho here, right? But it can be rho, can be bounded by rho. Okay. So we'll try to see what is the explicit rate of convergence. So, but using whatever the things we have seen now, I can state the next result. It's just that I'm going to summarize this convergence part. So I'm going to state this as a theorem. So let me call it theorem 1. So I'm going to assume that G is, so these assumptions are going to be similar to what we have in the previous statement, in the previous lemma. Assume that G is continuously differentiable on the interval AB and G takes the interval AB to the interval AB. Further, I'm going to take this quantity rho as the maximum of absolute value of the G prime of the X over this interval AB. And we take that to be strictly less than 1. Okay. Then, so the first thing is that X is equal to Gx. This has a unique solution in AB, in this interval AB. Secondly, for any choice of x naught in this interval AB, if we generate the sequence of the iterates using the fixed point iteration, then the sequence xn will converge to x star. Okay, and we can also show that the error in the nth iterate is nothing but less than equal to rho raised to power n times x star minus x naught. And further, we can also find the order of the convergence explicitly. So it is going to be, so we can prove that this is nothing but G prime of x star. Okay, so basically what different we are doing in this theorem. So in the previous statement, I wrote that if there exists some row for which this holds, right? So I'm just going to give you the explicit expression of the row, that what I'm taking and what I'm assuming here, that row is nothing but the maximum of this, which is strictly less than 1. This is what the assumption is. And then the following statements hold. So what can you say? Like, is this part okay? The A part? Using the previous discussion,
Yes, ma'am.
one in the lemma 1.
Yes, ma'am.
Because see, it's just that I have given explicitly rho as maximum of the mod of g prime of the x over this, but this will also imply that g prime of the x is less than equal to rho for all x is in AB, and rho is also given to be strictly less than 1. So whatever the assumption we have it in the previous lemma, they all holds here, right? So x equal to gx is going to have a unique solution in this interval. And what about the iterative sequence? So for this also, the same steps what we have done here. We just use the row here, right? Which is strictly less than 1. So, and which is given to be the maximum of the g prime of the x. So the same arguments will hold here, because you will get this is as g prime of the sum giant x star minus xn. And this will be less than equal to rho, because rho is the maximum of all g prime of the x. Right? So this part is also okay. And this part as well. You agree with me? That it follows from the previous results as well? Okay, so what we have not seen is this part, this equation. So let's give it an equation number. Okay, I think this must be 3. So note that. Okay, let's give this as 3 and this as 4. So note that A, B, and 3 follows by using similar arguments as before. So let's try to observe whether we have the 4 also or not. So what is x star minus xn plus 1? So x star is a fixed point. So this is the same as g of x star, and xn plus 1 is g of xn. And now I'm going to use the, again, the mean value theorem. So this is the same as some g prime of the giant times x star minus xn, where giant lies between xn, x star and xn. Okay, so what do we have? We have, okay, so what we have to observe here is that so what will happen to the sequence giant as xn tends to x star? So note that as xn tends to x star, the giant will also tend to x star, right? Because giant is lying between xn and x star. And I think with this step, once you realize that giant is also going to converge to x star, and g is given to be continuously differentiable, this means that g prime is also continuous. So as giant goes to x star, g prime of giant will converge to g prime of x star. So that basically concludes 4. Is that okay? Is this okay?
Yes, ma'am.
Okay, ma'am.
So from this relation 4, what we
Hello,
can... Yes?
ma'am. How ma'am Giant converges to X star?
Because you have a sequence Gin which is sandwiched between... So you have to see which is lower and smaller, but this is sandwiched between Xn and X
Okay,
star.
ma'am. Okay. Understood.
And the sequence Xn is converging to X star. So if it is sandwiched, Gin is sandwiched between Xn and X star, so this sequence will also converge to X star. Okay, you can take it as an exercise and try to write it down. That how will you prove it? Okay, so from here, what we can observe that. So you can also clearly observe the order of convergence, right? And the rate of convergence, right? So if we take G prime of the X star, this is not equal to 0, then what do we have from this equation 4? That this sequence converges from 3 and 4. Xn converges to X star. With order P is equal to 1. That is, we have a linear convergence. Okay. So note that I have taken G prime of the X star is not equal to 0. So if this is 0, then we will further see what happens. Okay, we'll get a better convergence than the linear convergence. Okay, so just keep that in mind that I'm taking G prime of the X star is not equal to 0. And the case G prime of the X star is equal to 0 will be discussed further. So in that case, what we will observe is that the convergence is not linear. It will have the higher order than 1. So, okay, still, if you want to see the statement of the theorem, I'm still having a lot of assumptions here, right? I want to just simplify everything and bring it down to the things related to the fixed point itself. Okay, so I'm just going to restate. Okay, and let me give another statement, and then we are going to see that whether we can use this theorem 1 to make sense of this statement, which I'm going to write now. So I'm just going to simplify some assumptions now. So this is a theorem 2. So assume that X star is a solution of X is equal to Gx, that is, it is a fixed point. And suppose Gx is continuously differentiable in some neighborhood around X star, together with the assumption that G prime at X star is strictly less than 1. Then my claim is that the result of last theorem, I'm not writing all the results here, that all the results of the last theorem, which is a theorem 1, so then the result of last theorem holds, provided X0 is chosen sufficiently close to X star. Okay, So what does this result basically say that suppose I have started with the initial guess x naught, which is sufficiently close to x star, and if we have that mod of the g prime of the x star is strictly less than 1, that is enough to ensure that the sequence of the iterates will converge, okay, and that will converge with the, so we have already seen the linear rate, okay, or the relation which we have obtained here. So this can also be obtained. So all these all these consequences what we have in this theorem, they all will hold in this case also. So let's try to see what we have to do. If we try to really use the previous theorem, so we have to bring down the things in that setting, right? So what are the requirements in this theorem? So we have to have an interval AB such that G takes the interval AB to AB, and we should have that the maximum of the G prime over that interval is strictly less than 1. So if these two conditions hold, then we have all these statements getting hold, right? So let's try to see if we can get hold on the interval AB, knowing the information that so what is given is that mod of G prime X is strictly less than 1. Okay, so I want to get hold on one interval for which I can say that maximum of G prime of the X is G prime of the X on that interval, let's call it I, okay, that is strictly less than, it might be less than equal to something, but I want that to be strictly less than 1. So how can we get hold on such interval I? So can you help me? We know that G prime is continuous. Okay, so note that G prime of the X star is strictly less than 1, right? So we can always find a number between 1 and G prime of X. So let's call that number to be rho. Okay, now can you just help me that how can we find an interval I so that we can say that G prime of X will be less than equal to rho for all xn in that interval?
Yes, ma'am.
Okay, you just have to complete this. How we have to find? You have to use the continuity of the G prime, okay, and that will ensure that so we can find, therefore we can find an interval, let's call it I, such that the maximum of the G prime of the X over that interval is less than equal to rho, which is of course strictly less than 1. Okay, so I want you to verify this statement. Okay, and let's call this I to be a epsilon neighborhood of X star. This is an epsilon neighborhood of X star. Okay, so we have found an interval I for which the maximum or G prime of the X for each x in that interval is strictly less than equal to rho, which is strictly less than 1, right? So now another thing we need to check whether G takes the interval I to I. If that holds, then we are done, right? We have got hold on one interval for which the requirement of the G are satisfied, and then we can use the previous theorem. So my claim is that we have the GI is contained in I. Why? So what we have to check, that if we take any x is in I, that is if I take x minus x star, this is less than equal to epsilon, then my gx is also going to be I. So we need to check whether gx minus x star, this is also less than equal to epsilon or not, right? So we can just simplify this again. So x star is nothing but g of x star, which is less than equal to some g prime of xi times x minus x star, which is less than equal to rho times mod of x minus x star, and rho is strictly less than 1 and x minus x star is less than equal to epsilon. This is going to be less than equal to epsilon, right? So if your x is in the epsilon neighborhood of the x star, then your gx is also going to lie in the same neighborhood, right? So we have that gi is contained in I. So I can apply the previous theorem. Okay, and note that this statement is also justified here because when we are going to generate the sequence, we are going to take x naught is in I, and then we will see that each of the xn is going to be in I. So x naught is in I, meaning it is x naught is a, so mod of x star minus x naught is less than equal to epsilon. So this means that x naught is sufficiently close to x star. Okay. So what it says that if you have to really verify whether the sequence of the iterates converge, it suffices to check that g prime of the x star is strictly less than 1. So you will be able to get, that will ensure whether the sequence of the iterates converge or not, right? Is that okay? Are there any questions here? Okay, if not, then let's try to take back these different choices of the G which we saw here. So we had different choices of the G here, right? And let's try to apply the information which we have got, which will ensure the convergence, right? So let's take this example again. So I'm going to take same example with a is equal to 3, right? So we have fx is equal to x square plus x minus, sorry, it was x square minus 3, right? X square minus 3, and we have to solve this equation, and we know that the root is 1.732, I mean, which is root 3. And what are the choices of the G we had? So we took the gx as x square plus x minus 3, right? That was the first choice. And second choice was 3 divided by x. A is 3 here. And third choice was 1 by 2 x plus 3 by x. So let's try to check that for which choices of the G we can have the convergence of the fixed point iteration method. So what will happen? What we have to check is that we have to find the derivative of the g. You can check, first of all, whether the g is differentiable, right? And we simply need to find g prime of the x star. So x star is this here. Sorry. This is the x star here. So what is the g prime of the x star in this case? So
Root 3 plus 1.
Greater than 1.
2 root 3 plus 1, and which you can see this is strictly greater than 1, right? So I will also give the argument that if you have g prime of the x star is strictly greater than 1, in that case the sequence will not converge. Okay. And in this case, what will happen? G prime of the x star, which is going to be minus 3 divided by root 3 square, which is going to be minus 1. So in this case, mod of the g prime of the x star is equal to 1. Okay. So what we have proved that if it is strictly less than 1, then the convergence is guaranteed, right? And I will give an argument for the case g prime of the x star is strictly greater than 1. I'll just try to show that in that case the sequence will not converge. But in the case of mod of g prime of the x star is equal to 1, you cannot conclude anything. Okay, so this case is not convergent. In this case, iterations will not converge. And in this case, it's inconclusive. So the sequence which you will generate using the fixed point iteration method, that might converge and that might not converge. Okay, and even if it converges, you can try to observe that it will converge very slowly. So you will have just mod of xn plus 1 minus x star. This is strictly less than mod of x star minus xn, because mod of g prime of the x star is equal to 1. Okay, so even if it converges, it will converge very slowly. So that is going to be of no use. And what happens in this case? So what is g prime of the x star? So this is going to be 1 by 2, 1 minus
0.
3 divided
0.
by root 3 square, right? So this is going to be 0. So this falls in our setting that we have, we want that mod of g prime of the x star is strictly less than 1. So in this case, we will have the convergent sequence. So this is, what is this case? The last case is when we have gx is defined as x minus fx divided by f prime of x, right? So if you, with this choice of the g, if you try to observe the fixed point iteration method, which is nothing but xn plus 1 is equal to g of xn. So what is g of xn? It is xn minus f of xn divided by f prime of xn. So I think you guys already recognize this method.
Yes, I'm Newton decimal.
This is the
Newton method.
Newton method, right? So this choice of the g, this just gives rise the Newton's method, right? We also used Newton-Raphson, meaning NR method, right? So, but in the Newton's method, we observed that the convergence order of convergence is 2, right? But here, so far, we have observed only the linear convergence. So there's something we are missing here, right? So here, in this case, that is when we take this as your g. So in this case, you can clearly see that g prime of the x star is equal to 0, right? So there's something happening when your g prime x star vanishes. So this we are going to see in next theorem, that we can observe the higher convergence of these fixed point iteration method under certain conditions. So these are nothing but higher order methods. And then it will justify that with this choice of the G, you get a Newton's method, which is going to converge with the order 2. Okay, so higher order methods. So again, we are discussing a one-point iteration method. So this I'm going to state as a theorem. So this is a theorem 3. So again, I'm assuming that X star is a root of X is equal to Gx. And G is P times continuously differentiable for all X near to, that is in the neighborhood of X star. And P here is, let me write the range of the P also. P times differentiable, and I'm taking P here as greater than or equal to 2. Okay, and further, assume that G prime of the X star, this is equal to 0. G double prime of the X star, this is equal to 0. That is all the derivative of G up to the order P minus 1, they vanishes at X star. Okay. In that case, if we choose initial guess near to X star, then if the initial guess X naught is chosen sufficiently close to X star, the iterative sequence given by xn plus 1 is equal to gxn, this will converge. This will have order of convergence. Of course, the sequence will converge and the order of convergence will be P. And we can explicitly find the limit of X star minus xn plus 1 divided by X star minus xn raised to power P. This is going to be minus 1 raised to power P minus 1 Gp evaluated at X star divided by factorial P. Okay. So first, let's try to understand the statement itself. So far we have just seen that the sequence of the iterates which we construct using the fixed point iteration, under what condition that sequence is going to converge, right? And so for that we got this criteria that if we check mod of G prime of the X star is strictly less than 1, that basically gives that the sequence will converge. Okay. Now here, this additional information I'm supplying that G is P times continuously differentiable, and it's all the derivatives up to the order P minus 1, they vanishes at X star. Okay, if that happens, then this iteration method, this will have the order of convergence P. Okay, so as an application of this theorem, you will be able to see that what is going to happen in the case of the Newton-Raphson method. So let's just try to observe. So in the case of the Newton-Raphson method, we have Gx is Fx minus Fx divided by F prime of X, right? So now we just have to find what is happening with the G prime. So start is the fixed point of G. So let's try to see what is happening with the G prime of X. So this is going to be 1 minus so I will get the first term as F prime of the X square
whole square
minus Fx into F double prime of the X divided by F prime X square, right? And if I evaluate this at X star, what will happen? So we have 1 minus. If you simplify this, let's just simplify first, then we just substitute it. So if we simplify this term, F prime of the X star will get cancelled. So we are left with the Fx into F double prime X divided by F prime of X square. Okay. So if you substitute X is equal to X star, what we get is that F of X star into F double prime of X star divided by F prime of X star. Okay. And F of X star is anyway 0, right? So this is going to be 0. And you can also find what will happen to the G double prime of the X star. So this will be F double prime of the X star divided by, okay, you can find it out. I think it will be just F prime of the X star. Okay, which does not have to vanish, right? Because it's depending on the F double prime. So it's not necessarily 0. So clearly what do we have is that with this choice of the G, the iteration method which we will construct, that will converge with what is a consequence of this theorem? So we have that G prime of the X star is 0, but G prime of double prime is not equal to 0. So P is going to be 2, right? As a consequence of this theorem. So therefore, by this theorem 3, the Newton's method converged with order P is equal to 2, right? So this is the application of this. Now let's try to prove this because the proof is very easy. So proof of theorem 3. Okay, so now you first of all tell me that whatever the assumption we have in the theorem, using that, can we say that the first thing is that X is equal to Gx, this has a unique fixed point and the sequence xn is equal xn plus 1 is equal to G of xn, this converges. So can we say these two things?
Yes, ma'am.
So again, you have to use the theorem number 2. So for that, we just need that for the theorem number 2, we just need to make sure that G prime of the X star is strictly less than 1. Right? Absolute value of the G prime of X star is strictly less than 1 and X naught is chosen sufficiently close to X star, then we have that using the theorem 2, we can make sure that we will have an iterative sequence which will converge, right? And of course, you can make sure the existence and uniqueness of the fixed point. Okay, so what we have to answer the question about that the convergence will be of order P. So that is, we will try to observe this relation. So what we are going to do, so what is given to us is g prime of x star, this is equal to 0, g double prime of x star, this is equal to 0. That is a derivative up to the order p minus 1 at x star, this is equal to 0. And g is given to be p times continuously differentiable. Right? So I'm simply going to apply, I mean, the only thing where I can think of applying all the derivatives is the Taylor's theorem. Right? So I'm simply going to apply the Taylor's theorem so that I can make use of this information. So I'm going to expand g prime of xn, sorry, gxn using the Taylor's theorem. So expand gxn around x star so what I will get, so this will be the same as g of x star plus xn minus x star g prime of the x star, and the second last term I'm going to have it as xn minus x star raised to power p minus 1 divided by factorial p minus 1. P minus 1 its derivative of g evaluated at x star, and the remainder term is going to be xn minus x star raised to power p divided by factorial p gp at sum xi n for some xi n lying between
xn and x star.
xn and x star. Okay. So now we already know that this term is 0. All the terms up to the order p minus 1 with derivative of g evaluated at x star, they all are 0. And what is g of xn? In the fixed point iteration method, it is nothing but xn plus 1. Right? So xn plus 1. And what is g of x star?
X star.
Star. And what is the, we are just left with the last term. So this is xn
Remainder.
x star raised to power p divided by factorial p into this term. Okay, so or I can write from here what is x star minus xn plus 1. This is minus xn minus x star raised to power p divided by factorial p gp evaluated at xi n. Okay, and from here I can get that x star minus xn plus 1. So I'm taking out the minus sign from this vector, so I will get x star minus xn raised to power p. So I'm taking out minus 1, so minus, so it will be minus 1 raised to power p, and minus is already sitting here, so I can in fact have the p minus 1 here. Right, factorial p gp of xi n. Okay, now you just have to take the limits both sides. So at xi n is lying between xn and x star, and xn is converging to x star, so we will have xi n is also converging to x star. So gp of xi n will converge to gp of the x star. Okay. All right. So we are going to use this result further. So we what we will observe that that so far we have, like in the case of the Newton's method, we got the order of the convergence to be 2, right? And same with the secant method, we got 1.62. But what happens that we just assumed, we were having this assumption there, right? If you recall, we were assuming every time that f prime of x star is not equal to 0, right? Which means that we were taking it as a simple root. So when we were talking about x star is a root of f, we were just always talking about the simple root. That is, the multiplicity of the root is 1, right? So if you do not consider this as, I mean, in case if you have that f prime of the x star is equal to 0, or maybe its higher order derivatives also vanishes, which means that x star will have the is a root of multiplicity higher than 1. In that case, the Newton's method will not converge with order 2. Okay, so we will use this fixed point iteration method itself to conclude certain things about the Newton's method when the multiplicity of root is higher than 1, and then how to rectify those methods to get the higher order of convergence. Okay, so these things we will see in the next lecture. So, but mainly we are going to use this result, the last two theorems which we have worked out here, that when we expect a higher order of convergence and what is the requirement for the convergence of the fixed point iteration method. Okay, so these two are important theorems which we will be using further. So if you have any questions here, you can ask now. Okay, if not, then we will stop here.